Hello, we are Team 1. Last week, our team reviewed the Katara Tower's tender document. In this process, we were able to identify the entire timeline of the construction project, as well as the companies that were involved in the project and their respective roles. However, there were also some important issues we did not discuss in our last video, one of which was about the project management. Before we delve deeper into our topic of today, earthworks, we would like to first discuss about the project management of this construction project. Over the years, project management has become complex with the global requirement for effective controls over design and documentation accuracy, project management costs and schedules, and the need to hand over an operational project that is an exact representation of client's vision. The company that was in charge of the project management of the Lusail Twin Towers project was Katara Project Management Company, or QPM for short. Now that we know who's behind the management, let's look into the contents. The first and the foremost part of the management is pre- and post-construction project management. This part includes feasibility studies, project execution, contracting strategies, tender document review, assessment, and recommendation up to the contract award and formation of criteria for the project handover to operating groups. The second part is cost estimating and control systems. This part is made up of development and maintenance of budgetary control and forecasting systems, providing significant input that enhances value engineering, VE exercises, and financial management of project funds and budgets. The third part is risk management, which consists of development and implementation of effective risk management strategies and processes by collaborating with designers, engineers, cost consultants, equipment suppliers, and construction contractors, and identification of risks and risk owners to develop action plans that reduce the level of risk exposure. The fourth part is schedule and time management, which includes development of project execution plans (PP), that includes important milestones and provides regular updates of PP, implementation of systems that create effective forecasts for milestones and project completion, and participating in recovery planning when a critical event has occurred that can cause delays. The fifth part is quality management systems. This part is comprised of status review, corrective actions, and electronic document management. The sixth and last part of the management is commissioning management service. This part is made up of management, coordination, planning, and control of all MEP testing and commissioning activities, providing an independent advice center on testing and commissioning activities, and managing the production of operation and maintenance manuals. Now that we have gone through the project management process, let's move on to our topic today, the earthworks. Atkins, the company in charge of the earthworks in that location, said that the earthworks was rather complicated and difficult because one hotel was located near the coastline, while the others was located far from it. Because the moisture and salinity can damage and weaken the structure, earthworks that take place near the coast is considered to be much more difficult compared to earthworks that take place far from the coast. The term earthworks refers to the procedure taken from the construction of underground substructures. This is done by first excavating down the required ground level, then building whatever substructures necessary, followed by refilling the holes. One major example of earthworks is dewatering. In construction, an uplift pressure can be exerted upon the building due to the underground water. This can cause the building to either rise or float, possibly incurring a disaster. To prevent this, after the excavation, a drain layer is created so that the underground water can escape through the drainage. This process is called dewatering. Since big buildings such as Katara Towers are more susceptible to damage from changes in underground water levels, we were almost certain that the construction of the Katara Towers would include the process of dewatering. However, we were unable to find any records of dewatering process that took place in the construction of the tower. Because of this, we decided to resort the record of dewatering process for another building with similar terrain and subterranean features. The construction project for a highway in Lusail, Qatar, otherwise known as Project P003 Lusail Expressway, was chosen as our model for our research. Hyundai Engineering and Construction was contracted by Qatar Public Works Authority for $1.21 billion. The construction began at May 2012. The dewatering system within the construction site were to be built in the excavation sites of Pearl, Uneza, and Wada. In order to proceed with the dewatering process, an investigation of the terrain is essential. In Qatar, however, there were several different factors that acted as a hindrance to apply common construction methods. This includes higher underground water levels due to the sites being close to the coast, irregular subterranean features such as underground cavities and joints, and even customs for dewatering. The fact that the ground is made up of limestone is also a setback as it increases the inflow of water into the underground cavities and joints. Upon further investigation of this limestone, we were able to determine that it is Simsima limestone that makes up the stratum found in large areas in Qatar. Based on how much weathering took place, the limestone was classified into 3 categories as shown in the table. Hardness and special properties were applied differently in each of these categories. Through this process, we were able to determine the permeability coefficient of the site, and since we were neglecting the effects of irregular subterranean features such as underground cavities and joints, we made sure that more dewatering would happen than what is prescribed from the underground permeability coefficient. The spare cavity in this case is between 2 to 3 times the prescribed amount. To achieve this, a method called deep well method was used. However, because the uncertainty caused by irregular features, a sump pit was used alongside this method. If the deep well method was a likely method used to the construction of the towers as well, the effectiveness of the method comes into question. In the case of the deep well method, it works well under high hydraulic conductivity conditions. And when compared to other methods that also work well under the same conditions, the range of capacity for the total system is very high, ranging up to 227,125 liters per minute, 60,000 gallons per minute, or 1,429 oil containers per minute. Because of this, it is fit for big-scale constructions like highway constructions. However, the deep well method also shows poor performance in silt and clay sand areas and stratified areas. Judging by this, though the deep well method was used to mass draining in the highway construction project, it is not recommended to be used in Lusail, where the ground is stratified. Considering many factors, not excluding unit cost, especially considering the ground in question is made up of stratified soil, the dewatering method of choice is unlikely to be deep well method and more likely to be well point system. Now that we covered the basis of the earthworks, the dewatering, let's see what other methods were used to complete the earthworks. We investigated what earthworks took place in Katara Towers and what constructions were undergone to overcome the problems. First, they used Sika-proof A+ 12 FPO sheet membrane for pre-applied, fully bonded below ground waterproofing. Sheet membranes were installed on both inner and outer walls of basement floors to prevent moisture and saline penetration. These waterproof membranes create dual bonds with fresh concrete, the 2 bonds being mechanical and adhesive. This in turn protects the concrete from moisture and salinity. Second, they use a special type of concrete made from the company Gulf GRC. Ultra High Performance Concrete (UHPC) is a cementitious concrete material that has a minimum specified compressive strength of 17,000 pounds per square inch. With specified durability, tensile ductility, and toughness requirements, fibers are generally included in the mixture to achieve specified requirements. The UHPC matrix is very dense and has a minimal disconnected pore structure, resulting in lower permeability. The material's low permeability prevents the ingress of harmful materials such as chlorides, which yields superior durability characteristics. Lastly, they built seawalls to protect the buildings. Seawalls are structures built to protect the coast from waves and minimize erosion. They absorb and disperse the ocean waves' energy to decrease the waves' destructiveness. These rules help protect the Katara towers from harm. And we'll explain in detail later on how UHPC was specifically utilized. This was Team 1. Thank you.